And yeah, thank you for the opportunity to come here and introduce Carbfix and what we are up to in Iceland. We are all aware of why we are here, but in Iceland we get annual reminders with the retreat of our glaciers, which really keeps us on our toes. And this is a former glacier called Ok, and it is the first Icelandic glacier to lose its status as a glacier. And there was a ceremony when the glacier lost its status, and this shield was put up next to it, and it says, "A letter to the future. Ok is the first Icelandic glacier to lose its status as a glacier. In the next 200 years, all of our glaciers are expected to follow the same path. This monument is to acknowledge that we know what is happening and what needs to be done. Only you know if we did it." So I think this is a quite powerful reminder that we certainly know what is happening and what needs to be done. And hopefully we manage to do exactly that. So another thing happening in Iceland is Carbfix. So Carbfix turns CO2 into carbonate minerals via reactions with volcanic rocks, and we have proven that this happens in less than 2 years at ambient temperatures. I also always like to bring this photo up quite early on. So this photo was actually taken 11 years ago. This is the night when we finally got the first fraction of CO2 into the ground. So this is, of course, in January, of course, in snowstorm, and of course, in the middle of the night, and probably on a weekend. And it's also in 2012, in the midst of the financial crisis in Iceland, hence the size of the champagne bottle that the team could afford at that point. Yeah, after blood, sweat, and tears, we managed to crack the code on how to inject dissolved CO2 into basaltic rocks. And since then, we have injected over 95,000 tons. We have demonstrated the world's first combination of DAC with CO2 storage, so direct air capture, in 2017. We have collaborated with over 30 universities and research institutes, published over 100 peer-reviewed papers, and currently we have 3 operational injection projects and 1 in commission. So Carbfix actually started as a research project. It was founded by Reykjavik Energy together with the University of Iceland, Columbia University in New York, and CNRS in Toulouse. So this was back in 2007. In 2012, we started the infamous pilot injection after so many attempts and so many disappointments. Finally, we got to the pilot phase. We injected some 175 tons of CO2 at that point in time. We managed to prove the rapid mineralization of the injected CO2. And then in 2014, it was decided to scale up the operations. So we've been injecting CO2 from a geothermal plant in Iceland since then. And people are often very surprised, why are we injecting CO2 from geothermal? Geothermal is renewable energy. Well, we do have some CO2 emissions associated with it, about 3% of what we would have if we were burning fossil fuels, but still some amount, so some 40,000 tons from this plant, and it's relatively easy to get rid of it, so why not do that? Also, since the Icelandic energy systems are almost completely renewable, this is actually one of the CO2 emission sources that Iceland needs to tackle to achieve the climate targets of the country. So in 2020, it was decided to spin Carbfix into a subsidiary of Reykjavik Energy, We started 4 at that point. We are about 40 today. And I'm going to give you an overview of what we are doing. So in short, mineral storage of CO2 is an alternative approach to the conventional CCS. It extends the applicability by enabling storage in reservoirs that have previously not been considered. What we do is that we dissolve CO2 in water prior to or during injection, and this means that we achieve instant solubility trapping. So we don't need a cap rock. There is no buoyancy of this CO2 charged fluid, which then reacts with basalts and forms stable carbonate minerals. And these rocks can be found in various places on all of the continents, of course most of the oceanic floor, and in fact basalt is the most common rock type on surface on Earth. So the possibilities are in many locations, but if you can spot Iceland in this, on this map, it's over 90% basalt, which makes it a very good spot to develop this method further. A little bit on the technology side. So we have 2 ways of injecting the CO2. So either we do downhole mixing of CO2 and water. This is when we have a pure phase of CO2. And that means that we do not need to pressurize the system. So it uses a very low amount of energy. If we have some less pure gas streams, we can dissolve the CO2 on surface, vent out the less soluble gases. This is, for example, what we are doing in relation to the geothermal plants, and we'll also do in a scale-up project together with the direct air capture company Climeworks. And then we inject the dissolved fluid. And this is what it looks like in reality. So as a part of developing this method, we of course also needed to develop some tools to monitor the injection, because we cannot use the conventional methods of monitoring pure phase injection. And what we rely on is geochemistry. So we sample the subsurface fluids. We use tracers, both natural tracers and tracers that we add to our injection. We calculate mineral saturation states, etc., and do a lot of mass balance calculations. In 2021, we got our methodology verified by DNV. So this is the first third-party verification of this kind of a method. This methodology is available on our website if people are curious. And it's kind of built with the CCS directive in mind, so the guidance documents of that, kind of trying to apply the same concepts to a very different method, which is kind of what we are always doing. So this is the pilot site in 2012, filled with snow as usual. So we did not really make our lives too easy. One of the reasons was because we could get very cheap CO2 in January, because usually there is excessive CO2 after the Christmas, so people have stopped drinking beer and stopped drinking soda. So we could get fairly good price, but that at the same time meant that we were going to the mountainside in Iceland and doing a scientific pilot in this pile of snow. But the results, over 95% of what we had injected was mineralized within 2 years. We published the results in Science in 2016. Following the success, we started the injection from the power plant. This is Gertrud, our capture plant in Hellisheiði. And there we have now injected over 95,000 tons, targeting retrofitted reinjection wells that belong to the geothermal plant. But a little bit more on how to close the chain. So we have these 3 pathways to close the CCS chain, and we are exploring all of them currently. So first of all, the on-site capture and storage. This is, of course, always the most economically feasible way of storing CO2. We are now working on building a larger capture plant at Hellisheiði. So we will be able to capture all of the CO2 from the Hellisheiði power plant from 2025. This is a project called Silverstone, funded by the European Union Innovation Fund. And there we use only water to capture, and we have managed to demonstrate through a pilot over 95% capturing efficiency of this scrubbing tower. Second of all, when you don't have a formation next door to your emitter, of course, as we've been discussing through the path of this conference, a hub to receive the CO2 is the solution. And we were granted the large-scale innovation fund in 2 years ago, and are now working on building the first of a kind mineral storage hub in Iceland. And we anticipate to start operations by the end of 2026 with a capacity of 500,000 tons of CO2 per year. And then thirdly, for the emissions that we cannot capture and emissions that have already taken place, we have the direct air capture technology. And there we have moved from the capacity of 50 tons in 2017 in Project Arctic Fox towards 4,000 tons per year in 2021 in Project Orca, and are now preparing for a scale-up to 36,000 tons per year, starting commissioning next year. And this cannot be done without continuous research and development, and this is what we emphasize quite a lot at Carbfix. We work on different R&D aspects in parallel. We try to fast-track everything that has potential, and our research collaboration is the cornerstone of our R&D work. One project to mention is the project CO2 Seastone, which we are now in commissioning phase. So this is a project where we are going to inject with seawater. So we have done some extensive lab experiments as a part of a EU-funded project that ended in 2020. And now we want to go to the field and see what happens in reality. And also, as part of this project, we actually managed to demonstrate the first cross-border shipping of CO2 from Switzerland. This was completed end of last year. And this was, for me, as a geologist, one of the most interesting pilot projects that we have done. So we shipped a container from Bern, put it on a truck, put it on a train, and put it on a ship, and then also then again on a truck to our injection site. Before we did this, we had, of course, asked a lot of people what happens if we want to ship CO2 for storage in Iceland, and we got answers, and this was supposed to be quite straightforward. But turns out the man-made systems are sometimes even more complicated than the natural ones. And this is what we are dealing with now. So the CO2 arrives in Iceland. We get a very strange phone call from a very confused guy at customs, trying to figure out how he should categorize the CO2. So this results in some phone calls to the environmental agency, back and forth, a lot of lawyers, a lot of confusion, and in the end, the Icelandic agency exempts the project from waste regulations, since this is an R&D project. but it could not be processed in accordance with the CCS directive because it's not a commercial project. Okay, so we finally get the container at the site, we inject the CO2, and then we are supposed to return the container back to Switzerland. Then the story continues. So the Icelandic Environmental Agency talks to the Swiss federal offices. They go back and forth. Since the CCS directive is not implemented in Switzerland, they cannot use that as a base for their regulation. So in the end, they decide to categorize the CO2 as waste. So the container was stuck in customs at Switzerland for a long time because being categorized as waste requires permit and quite a lot of bureaucratic work. So not only we need to figure out how to model our faults and assume that we don't have too much of a leakage from our reservoirs, we also need to figure out how to work around the man-made systems. Finally, I just want to mention or give a little bit of a shout out to the research institutes and universities that we are working along with. As I said earlier, we have co-published over 100 scientific papers to date. 9 PhD students have finished their Carbfix related projects. I was one of them, got to do a project on this pilot that we carried out in 2012, so a lot of shoveling through snow and filling of water bottles. And we currently have 2 students working on the projects, finishing next year and the year after. So a lot of exciting things coming out there. And this is, of course, very important to accelerate all aspects of our technology, get some new perspectives, and also get more people to work in this field. So that's all for me. Thank you.